Calculations and significance. We are looking how to determine significant figures from calculations. There are multiple operations that we will do in calculations, and the different operations will have different rules for determining significant figures. For a basic addition or subtraction problem, we will carry our significance through the calculation based on the number of decimal values in the values that we're working with. So for example, if we want to add the numbers 58.43, 1104.78932, and 607.0139, we would add up our numbers and arrive at an answer of 1770.23322. Notice that in this example, I have labeled x's in two of the numbers. The x represents the absence of precision in the values containing the x. What that means is we do not know for certainty that those x values are actually 0. They could be 1, they could be 3. There is no way of knowing, based on our level of uncertainty and the level of precision in the measurement, what the value of x is. So if we take these three numbers, put them in our calculator, we will get this answer. However, we are not able to calculate an answer which has greater precision than the values that went into it, because that would be ludicrous. It would be this idea that somehow we're able to know for certain what those x values are when we don't know their value. So the way that we will keep track of significance in an addition or subtraction problem is to limit the significance of our answer to the number of decimals in the number going into the computation, which contains the fewest decimals. Of these three numbers, 58.43 has the fewest decimals, so we will limit our significance to the number of decimals in 58.43, which is, of course, 2. We round our answer to that level of significance, and so our actual answer then is 1770.23, rounding after the second decimal place. This works for addition and subtraction because in addition and subtraction problems, our decimal never moves. However, when we look at multiplication and division, we find that the decimal will move in a multiplication or division problem. This means that we're going to have to use a different system for keeping track of significance for multiplication and division. We base our significance for these problems on the total number of significant figures in the values going into the operation. So for example, if we multiply three values, 12.238, 1.2 times 10 to the negative 4, and 0.000458, when we multiply these three, we wind up with a value of 6.726005 times 10 to the negative 7. Because the decimal moves throughout this, we will use the number of significant figures in the number with the fewest significant figures. Of these three numbers, 1.2 times 10 to the negative 4 has the fewest significant figures. So because there are only two significant figures in that second value, we limit our answer to two significant figures, which means that instead of 6.72, etc., we have 6.7 times 10 to the negative 7, or 0.00000067. Exponents follow the same rules. If we were to exponentiate a number, that's the same as doubling, or squaring, or cubing, or any other operation of that sort. Because we're going to be multiplying a number by itself, the number of significant figures in those exponentiations will be equal to the number of significant figures in the original term. So, for instance, if I take 8.134 times 10 to the negative 2 and I cube it, we wind up with a final solution of 5.747 times 10 to the 8. We still have four significant figures like we started with. Same is true if we take that number and we take its square root. We'll wind up with 2.883 times 10 to the 1. For those who are not familiar, taking an exponentiation of a fraction like 1/2 or 1/3 is a way of taking a square root or a cube root based upon what the value in the denominator of that fraction is. 1/2 is a square root. 1/3 would be a cube root. Looking at logarithms and antilogs, these are specific values that are useful for a lot of applications. One of them is pH, which is something that's talked about in Gen Chem 2. Logs and antilogs will reverse each other. If I take the log of an antilog, I will reverse the antilog. If I take the antilog of a log, I will reverse the log. We look at these logarithms, and they seem to actually defy the significant figure rules that we just talked about in multiplication and division. But the reason for that is because a logarithm conveys two different types of information. There is information about the measurement itself, and information about the location of the decimal in the measurement. The number of decimal places that we will keep in the answer of a logarithm calculation will equal the number of significant figures in the original number. If we take, for example, the log of 4.01 times 10 to the 5th, that gives us an answer of 5.603144. We would keep 5.603, which has 3 decimal places and a total of 4 significant figures, or so it seems. But remember that significance is based on the number of decimal places, independent on the values before the decimal place. Having 3 decimal places indicates 3 significant figures in the original number. If we take the antilog of a number, antilog of something like 12.038, we will take an antilog by taking 10 to that number. So 10 to the 12.038 gives us 1.09144 times 10 to the 12. The same rules apply. The original log had 3 decimals. And so if we take 3 decimals, that gives us 3 significant figures, which means that we will keep 1.09 times 10 to the 12. Now, when we look at combined operations, these are operations which contain either combinations of addition and subtraction with multiplication and division in some way, shape, or form. So maybe an addition with a multiplication, or a subtraction with a division, or any of these kind of combinations. Because addition-subtraction rules differ from multiplication-division rules, we have to convey significance through a series of different types of operations. We will use the order of operations to determine how our significance plays out. We apply that significance as we work through the problem, and hold out generally more significant figures than we should in order to prevent rounding errors from confusing our problem in the end. So as an example, if we take 6.5893 and multiply it by the subtraction of 9.5837 from 13.1, so 13.1 minus 9.5837, and then multiplied by 6.5893, the order of operations indicates that we should do our subtraction first. So the first thing we'll do is subtract 13.1 minus 9.5837, which gives us 3.5163. Now, because the original number, the 13.1, has only 1 decimal place, we can only keep 1 decimal place in our answer, which would round us to 3.5. But we're going to hold out more decimal places for the sake of preventing rounding error. So we will mark where that significance actually is in this fashion, and then use it in the next operation. If we take 6.5893 and multiply it by 3.5163, we get an answer of 23.16995559. Now, our original number that we multiplied by, the 3.5163, was only allowed 1 decimal place, which would limit its number of significant figures to 2. So we're limited now to 2 significant figures in our final answer, which means we will round at the second value in the number, rounding to 23 as our final answer.